Hello, Professor. This is Group 5 and Group 8, and our group topic is Hadoop ecosystem for crop yield analysis prediction optimization. And this is our content. For the background and value to meet modern agricultural resource optimization need, we are using 1 million structured crop data process paired with the Hadoop ecosystem. This lets us analyze massive data efficiently, laying a foundation for practical production decision. For the research objective, first identifying and verifying crop yields, key influencing factors will ensuring constant analysis result. Second, assess the stability and generalization ability of regional yield prediction models. Third, quantitative compared how different Hadoop ecosystem components fit various tasks. For the problem statement, first, which factors affect crop yield, and do half and spark analysis result agent? Second, is a regional linear regression model better than a global one? Third, how do HDFS, half, spark, and HBase perform in storage analysis and modeling tasks? Next.
This slide shows our overall workflow and tool selection. We start by storing the large structured dataset in HDFS. Hive is used for batch analysis, such as correlation calculation. Spark is then used for machine learning tasks because it is fast for iterative computation. Finally, model results are stored in HBase for fast retrieval, and the results are visualized using Power BI. Each tool is selected based on the task it performs, not just to include more technologies. We conduct some experiments to determine the selection of the tools, as shown in the table. It presents the reason for our choice of each tool. Next page.
We adopt a 3-layer architecture: HDFS for data storage, Hive for structure querying, and HBase for fast result access. At the storage layer, HDFS stores both raw and clean CSV data. The raw data is preserved, while clean data is stored separately and reused by all downstream tasks. This separation ensures reproducibility and avoids repeated data cleaning. Hive is used to create external tables on top of HDFS, providing structured access without duplicating data. During cleaning, Boolean fields such as irrigation and fertilizer usage are standardized into numerical values to support analysis and modeling. HBase is reserved as a serving layer to store model evaluation results for fast retrieval and comparisons. And this layer design improves data quality control, collaboration, and downstream analysis efficiency. Next slide.
It's our findings on global factor priority using Hive and Spark. First, our data shows a clear hierarchy. Both models confirm that rainfall is the dominant factor. It has the highest correlation, significantly outperforming irrigation and fertilizer. Other factors like temperature have almost no impact. Second, the results are remarkably stable. For crops, average yields are very uniform, with soybean and wheat performing slightly better. Geographically, this trend is identical in all 4 regions, whether in the west or north. Rainfall remains the #1 driver. In short, our analysis proves that rainfall is the absolute determinant for global crop production, regardless of region or crop type. Next page. Alright,
The analysis was verified using a combination of Hive, Spark, and random forest models. First, the data was loaded into Hive and grouped by crop type and region, with key variables aggregated into a structured table to ensure consistency and comparability. Spark was then used to calculate feature importance across different crops and regions to assess whether the influence of key factors remains stable. Next, random forest models were trained for each crop and region using fixed parameters, and their performance was evaluated using RMSE, R-square, and training time. Next page. Uh, the results showed strong consistency across the analysis. Rainfall was consistently the most influential factor, followed by irrigation, fertilization, temperature, and year. This ranking remained the same across all crops and regions, confirming stability at both levels. Although there were minor variations in training time and slightly lower R-square scores in some regions, the overall consistency of feature importance supports the reliability of the results and highlights areas for future model improvement. Next one. Alright, so in this part, our goal is to build a simple and interpretable baseline model to predict crop yield by region. Based on earlier analysis, rainfall is the most important factor while temperature and fertilizer also affect yield. Because different regions show small differences, we trained separate models for each region instead of one global model. We use linear regression in Spark MLib and this model is fast, easy to understand, and suitable for the Hadoop environment. The input features are rainfall, temperature, and fertilizer usage. For each region, we used the 70-30 train test split and evaluated the model using RMSE and R-square. The results are very stable across the regions. R-square values are around 0.78 and RMSE is also close to 0.78. The East region has best fit and the West region has the lowest error, but overall differences are very small. Finally, we save the evaluation result into HBase, which allows fast access for reporting and dashboards. In conclusion, the regional linear regression model is stable, interpretable, and easy to integrate, making it a strong baseline for future work. Yeah, that's all.
This part introduces our crop yield optimization strategy and its results. The goal is to improve crop yield by adjusting irrigation and fertilizer under different rainfall conditions. The strategy is based on prediction results and focuses on improving farming decisions. Rainfall is divided into three levels: low, medium, and high, using region-specific thresholds. Under low rainfall, irrigation and fertilizer are encouraged to reduce water and nutrient stress. Under medium rainfall, fertilizer is adjusted moderately. Under high rainfall, no action is taken to avoid wasting resources. Next page. We evaluated the strategy by comparing baseline predictions with policy-adjusted predictions. Results showed yield increases of about 16 to 68% under low rainfall, around 50% under medium rainfall, and no improvement under high rainfall. Overall, the strategy is simple, practical, and shows that rainfall-based decisions can effectively improve agriculture yield. Thank you.
This project has three key achievements. First, the results show that rainfall is the most important factors affecting crop yield, followed by irrigation, fertilization, temperature, and year. This rank is constant across different analysis tools, which confirm the stability and reliability of the finding. Second, the regional linear regression model outperforms the global model with an RMSE of about 0.78. This indicates better prediction stability and shows that regional differences are important for accuracy crop yield prediction. Third, the project successfully applied the Hadoop ecosystem to agricultural data analysis. HDFS handles data storage, have supposed based queries. Spark enable fast computation and modeling, and HBase provides quick access to key indicators. For future work, more detailed data, advanced model, and real-time processing can be introduced to further improve prediction accuracy and support the real agricultural decision making. Okay, thank you.